So yesterday we were working with the quantile regression forest, the script number 4. But if you have closed your R or the computer, then you lose all the environment, the objects of the environment. This is not a problem. So what we are going to do is to run the first 2 lines. So we remove everything that is here, and then we set the working directory again. Okay. We will load we will set these variables. Then we have to load the libraries. Then we load the covariates with the names and so on. So we run all these parts from the line number 57 up to 77. Then we load the data. So we need to run these lines up to the line number 94 or somewhere there is section 1.3, including section 1.3. And finally we run the section 1.4. So, and let me know if everybody was able to do it, and then I would like to to recall where we are, in what step we are. So, just to remind you, what we have done yesterday is that, so we put the soil data and the covariates data together. We created the calibration matrix. So this table with the soil properties and the values of the covariates. And then we said, you see here, this part is where we make the model. So we have to we set the parameter for the tenfold cross validation, and then making also the repetition. So it's repeated several times, tenfold cross validation, and the model calibration itself. Okay. So now we got the model. With the model, we were able to estimate the accuracy of the model. So now we have the overall accuracy. So this is the steps. And now we want to use the model to make the prediction. So this is what we are going to do. And for this, we have to go to, so we load all the data. What we could do is to run this again, but you know, it takes some time to fit each of the model. So instead of running the section number 2, so let's see. So the section number 2 is the selection of the covariate with random feature elimination. Then the quantile regression forest calibration is the number 3, and the 4 is the uncertainty assessment. We already did all this, and at the end of section number 3, we save the model. So we have the model in this line. We save the model in the disk. So we don't need to run everything again. It is already in our disk. So now we go to section 5, but here we need to load the model. Okay. So for this we need to the model was this one, so we no, not this one. So let me just save. We go to section 5. Then we go to the line number 207. And let me just modify this script. So this is the model that we produced yesterday. So we want to load it, and to load this model we need to. This is. Let me check if RDS. Yes, okay. The command that we have to use is this. So we are going to define an object model, and we will read this file. So we have to put the output folder. Within the output folder, models. Within the models, you select the model SOC 0230.rds. So this is in section number 5. Let me know if everybody can do it. Okay, so you have to see this here. Error? But assign it to the model. Yeah, here. That's okay. Yeah, and run it. Okay. Let's continue. So now in this step we are going to run the covariate. So we want to take a covariate, just one covariate, as a reference of the map that we are going to produce. So in this case we take from the list of covariates. So if we run, here we have 68 covariates, but in this way we select the first covariate. Okay, we only select only one. Okay, it's the bio one, so it could be another. Yeah.
So the first, let's see, there's a highlight and then there's nothing in this console. What shortcut do you use to make that happen? Like when you highlight a command, something in the console.
You mean?
You do covariates. Just wait for the console.
You can use the console. The console is a good place where you can try things.
I just want to shortcut, like you just click on the code. You just want to run it. You want to run the console. The C is somewhere. The C is somewhere enter. The shortcut.
the shortcut for the summary.
You highlight it, and then as you press something, and
Yeah. Okay. Yes, basically, I always use Control Enter. Control Enter execute the line. If you see here, I step here, so when I press Control Enter, it runs the whole line. But if you select, for example, this, okay, and then you press Control Enter, and then you see only it executes only the part that you select. If I select only this, it will run only COGS. So in this way you can run, for example, only this, for example, and this is the extent of the file. So
I was asking myself the same thing, and I saw him.
So in this case, this is creating, in this line we will create a raster with the extent of R of this object, and then with the coordinate reference system of R. Yes, so here we have all the parameters of the coordinate reference system. But this will have 5 columns and 5 rows, so it means that it has 25 pixels. So we want to use these pixels as tiles. So we will, because now we want to use, the model is already done, it's already trained, and now we want to use the model to make prediction at every location. But for some countries or for some resolutions, if you want to predict at the whole area, maybe you have a computer is not too big, so it is better to make tiles of the study area, and you make predictions tile by tile. So we will make a prediction for the first tile. So we have 5 by 5 tiles. So we take the first tile, so first box, we make the predictions in this area. Then we take the next box, we make the predictions there, and then we collect all of them and we put all together. Okay. This allows us to run the script even in we have done it in, for example, in a computer that was 4 gigabytes of RAM with small processor. So even though that it was slow, you don't saturate the memory and R doesn't crash. This is to prevent that R crash. Okay. So and then we use the function that basically this will create. Here we provide the raster that we want to split, the tiles that the raster with the pixels that we want to use, and this will overwrite, and the file name. So the tiles will go to output tiles and tiles.tif. So we run. Okay, we have an error. Okay. So let's see how it looked like.
How many tiles is it expected to make?
Sorry?
How many tiles is it expected to make?
25. 5 times 5.
5 times 5.
But you can decide, for example, maybe you want to create only one row, or maybe, for example, for Jamaica, maybe you want to make a tile, only one row and 5 columns. Okay, or for other countries maybe that are longer, maybe you want to do only 5 rows or 20 rows or as many rows as you want, and only 1 or 2. Okay, so you got error to create the tile. What was this the error?
Error in evaluating the argument text.
Let me, okay, yeah, let's see. Error in to do. And was R created? Yes, I think so. Let me check. No, was not created. Yeah, you have to run this line. I think. Yeah. Now check it again. Yes. Yeah. So the function tiles will. Was there any other question? No. The function tile. Let me show you. Script. We have in the folder output tiles. So here you see the tiles. Indeed, some of the tiles might have no data at all. Okay. So if we create 10, for example, 10 rows and 1 column, we will have 10 files here. Okay. So now we want to go to the next step, and here we are going to use a loop. And what the loop does, it goes from here until this part, okay? All this. This is a raster package solution in case that Terra result give NA only. So what we have to do here is we are going to sequence along the tiles. Okay, so sequence along the tile means that we are going to run this process 25 times. The variable that is created, so this is a for loop. Remember that a for loop runs the same script for many objects. For many, in this case it's for different objects, for different tiles. So first it free the memory. So let me just put here, you don't need to do this, but it's just to show you how it will work for the first tile, for example. So J will be equal to 1, so then Rust will be will read the first tile, so we can plot indeed. Yeah, so this is the area that is going to plot now to predict only on this. So we don't care about the values of this raster. This raster is only used as a reference for the parameters of the resolution, coordinates, and so on. Then we crop the covariates because to make the prediction, the model needs to use all the information from the covariates.
So on error, so there were 25 warnings. Use warnings to see the chip at top.
Warnings?
Yeah. It says there were 25 warnings. Use warnings.
Yeah, but if they are warnings, it's not a problem.
Okay.
Indeed, yeah. So here you can see the first 16 covariates. So the model, when the model used the covariate, when we fit when we train the model, the model used different set of covariates. Okay. Now we need to provide the values of these covariates for the study area, for the small tile, for every pixel that we want a prediction. So in this case, we are going to use. So for that reason, we first crop the covariates with the size of the tile. So if we check the content of this new object,
You have an earlier.
yeah. So now we have the values of all the covariates for this small area. Okay. And then we use the many packages has the function predict, as they also have the function plot, or many functions that have the same name, but when you for example, if I look here in the help, this is just for your information. You don't need to repeat this process. But if you look for the function predict, you will see that there are many packages that use that have the function predict. Let me caret. So well, it has been defined in many packages. In the case of Terra, if I use this. In the case of Terra, it recognizes an object that is a model. A model has to have certain parameters. Not any model, not all the models can be recognized. But if the model has certain parameters, the raster identifies the model, and then what it is going to do is to take the process of prediction, identifying each of the pixels where it has to make the prediction, and applying the prediction of the model to each pixel, and after this it will build a raster again. So it will this prediction function will give us a raster again. Sometimes you need to convert the raster into a table and make the predictions into the table, and then convert the table into a raster again. This is not the case now. So in this case, we will apply this function. This function uses the raster that we provide is all the covariates. The model is here within the model that we have. This is a model, quantum regression forest. It has to be you see, this is a random forest model, and it also has this class. So Terra recognizes random forest models. Okay, then this is to remove NA values, and it has to use this package, and we want to predict the mean value. Okay, so we just apply this, and now we can plot the prediction. So this is our prediction for. Wait a minute. So these are the values for the soil organic carbon. for this small area, and then we can also make a prediction of the standard deviation. So we run the same, but instead of predicting the mean is the conditional mean. Conditional is because it's a predicted mean. Yeah, it's the most probable value. And we can also make a prediction of the standard deviation. What is the standard deviation of each pixel? It will be the uncertainty that the prediction. So here what we have is the uncertainty of each pixel. Okay, you know, when you have a classification of a satellite image, you can make a classification, and you can see also the probability that this class belongs to the pixel belongs to this class. So in this case, this is something similar. This is when you get the higher value, it means that the uncertainty is higher. So then it means that we can create a map that will show you where you are more certain, where are you more uncertain. So it means that if you are in those areas that you get more highest uncertainty, you can go take samples and improve the map. So run the process again, and you will improve the map by including more samples in those particular areas. And then we'll write, here we just write the tiles, the predictions, and this just run all together. So what you have to do is to step here at the beginning of the for loop, and we just run everything with the control enter, or just with the run button, and you will see a message of each of the tiles that has been predicted here. It takes a while. Yeah.
Maybe I ran it before, but it says the
Path
plot doesn't exist.
doesn't exist. So let me see. Mean that.
So that's SOC.
No, in this set attribute folder doesn't exist. This is maybe should be within output, within tiles. No, it's not. No? Let me check if I have it. So in the output folder, tiles, you should have this folder soil attributes and aggregated tiles. So if you don't have them, you just copy from the Google Drive, or just create the folder with these names. Okay?
They're empty.
Yes, empty, because you are going to create the files. Okay.
Get
Yes.
an error when I'm trying to run the loop.
Error with plot.
For J in sequence along tile, it keeps saying unexpected symbol.
Oh, yes, because that's it.
It wasn't supposed to be in a line. Oh.
Yeah.
Oh.
Yeah, maybe you write a plot to plot something.
And then I probably.
Yes, yeah.
Yeah.
Yeah, you should go now. Yeah.
¿Por qué con el coro sale, en la mía sale?
Porque debe ser una de las áreas que no tiene datos. ¿Cuál?
Con lo coro es, tendría que salir
No, no, no.
Photocopilot,
No, porque acá, como comenzó el for, o sea, R va a correr el for cuando cierre el for cierra acá. Entonces, claro, entonces aquí tenemos que darle escape y correr todo de una, ahí, clic, y va hasta el final. Entonces ahí va uno por uno. No lo
está
sé.
corriendo, ¿verdad?
Sí, ahí está corriendo. Ahí te va a ir mostrando cada uno de los. Sí, ahí dale escape. Párate ahí en la consola.
Acá.
Sí. Apretá escape. Escape. Y ahora anda donde comienza el for. Ahí. O párate aquí y dale correr, run. Ahí va. Duplicate name since path raster. Ok, porque esto... ¿dónde están los archivos?
En mi desktop.
Aquí, quizás. Este lo vamos a... ok.
Interestingly, perfect.
Yeah.
The files, they look black and white inside of the folder.
Yes. Yeah.
But in R, you can actually see the files. You can see the maps, like all of them.
Okay, single band.
Yes, because they are replaced. I mean, what do you mean? In the here, you mean?
Yeah, I see them black and white there. But
Yeah, but this is the window. Is the window representation. If you open this with QGIS, for example, okay, this is for val density, but here you see some of the values. I think this is because if it is
No, but you had to set the colors. You had to say pseudo color, and then you said this. You said the thing because it's single band. It doesn't have a 3 RVG layers.
Okay.
So you have to give it pseudo color. So I guess ours have a
In
a
R, you
pattern
do
where
it. In R, you do
yeah,
it.
it's trying to default it. Yeah.
Colorize them.
Yeah, yeah.
Okay. I guess you'll be able to categorize them.
Yeah. Symbolize.
yes, this is, for example, this was one of the files that you see black and white.
Over the files.
Okay. Okay. Yes. Error. Duplicate names. Raster. Okay. This is. Let me check first that. We have to remove this. Okay. Now we go to the beginning. No, I don't want to do this. Okay, too late. Okay. Now we go to section 5. Here we load the model. Yeah, this will go. Okay. So after these tiles are created, now we need to merge all these files. Okay. So now we want to use. I will use the list file. This will create a list of the files that we have inside this folder. Okay, so you should have 25 files that are the 25 attributes. Tiles. This is for the case of. This is the mean prediction, and the second one is the prediction of the standard deviation. Then here I will create two lists that they are empty. Okay. And next we read each of the tiles. So basically this part read the file, create this object, and then we assign this object to one of the list. So it goes to the first element of the list. G in this case will go from 1 to the length of mean that are 25. So we are going to repeat this process 25 times. So it reads every tile and put it within the list. The list, because we cannot read with raster directly because they belong to different areas. So because they are actually the tiles. So we want to put all together, but we have to merge them, those tiles. And then we do the same with the standard deviation. And this is another function from Terra that basically creates, it's like it creates the list into an object that is a spatial, how is the name? Let me see, the name of this is for the spatial raster collection. SP for spatial raster collection, yeah. So we create a spatial raster collection with this list. It's just a transformation of the format, it does nothing. And here we have the mosaic function. So this puts all the tiles together. Very fast indeed. So we can plot this because it's our result. So plot prediction mean. Okay, this is our predictions. This is the prediction of the mean values. And we want also to see the standard deviation. So here you see that the greener areas are those that are more uncertain. So we can also see, we could overlap this with the points, and most probably we don't have too many points in those areas. That's why we get the green values. Also, all the samples here come from the agricultural fields. So it means that other areas that were not agriculture are not well represented. So we need to remove we can mask the areas that are not agriculture. So remember that we did the evaluation of the accuracy of the map. So we know the accuracy of the map, but this accuracy is valid for the area that is represented by the points. So if you are working in an environment, For example, you can have your points distributed in agricultural fields. And then you use the raster that covers the whole area, and then you make a map. And the map will also show the values for forest, for example, but you didn't include any forest data. So it means that the points, the predictions, you can get the prediction, but the accuracy that you have for those maps are only valid for the agricultural areas. Is that clear? No, I don't know. So what does it mean? Is that let me just do something to show where the points are. That we have that, yes. STRCF. No. Vect. And that we need matrix. Yeah. That latitude is, longitude is x, latitude is y, CRS is ESPG, or just, I always forget the acronyms. Is it there? 432.
Yeah, 4326. To reach is it 4326.
Where is the, I'm looking for the, okay, let me see if, EPSG, EPSG, it's okay. That doesn't has the okay, let me just read the plot. That thank you for your patience. That plot that are true. Okay. This is a distribution of points that we have used for the samples. So we can see large areas here that doesn't belong, that were not sampled. It doesn't mean that they are not well represented. Maybe they have the same features, for example, than here. When we see the distribution of the error, the uncertainty, and these parts are lower, and the greener part, even when you have some points, still are high. Okay, so the model is not able to find the real relationships between the covariates and the values of the points. So, but then we also have very large areas that maybe doesn't belong to the agricultural fields. So what we can do is just to remove the areas that doesn't belong to the agricultural land. Okay, why? Because we are not certain about the uncertainty that we give in the map, that we estimated, that was about 0.20. Well, this accuracy is valid for the areas where we have the points. Okay.
I'm sorry, but where in the map shows us that that area is agriculture? All I'm seeing is the deviation and the points. I'm not seeing I'm not seeing the land use.
We don't see the land use, but we have another land cover.
Okay.
We have a layer with the land cover, actually. So this is the next step, actually. So here we have the AOI. This is the area of interest. Basically, they will have this same shape. And we will just mask the area with this. In this case, it will have no effect because they are the same. Actually, it has the same shape. It is useful, this function, when you use a bigger area and then you want to cut it, for example, using a shape file. And this is the mask. So the mask shows the green part are the agricultural fields, and the other is the grasslands. So, and this is what we will do, is just to mask the area, to remove the areas that are not agricultural fields. Yes.
So the initial thing is get off of Google Engine, right?
You can, yes, you can do, yeah,
To get the NDV tips, the remote sensing tip.
the NDVI,
Yeah.
you mean?
Yeah, tip, just get that off of Google Engine, and then you're importing it.
Actually, what I did is to download. There are two links at the end of the script number 3, the presentation number 3, and the second script download the mask, and the mask refers to the agricultural areas. That was the previous raster, so that was obtained from Google Earth Engine. But you might have a map, for example, a shape file with the areas that belong to agricultural fields. But if you have points that are distributed in forests that represent all the land use, for example, then you can keep the whole map. Okay? So you don't need to mask everything. It is only in the case of the nutrients, the map of nutrients, that where we only use data from agricultural fields, then we mask the rest of the area. So we do the same with the standard deviation, and we can also predict, shows the coefficient of variation here. So this is the percentage of error. So in this case, we have a coefficient of variation lower than 20% in in these parts and higher values in these other parts. I think you miss these
I
two
missed
first
these
lines. Maybe. Let me. Yeah. Yeah. Yeah.
I missed this
Yeah. Yeah.
line.
Yeah. Just these lines. Yeah. And then we will save the results. In this case, we have a little bit complex, but actually seems to be very complex, but actually it's not. So this function, in this case, we didn't see the use of if, but the if is a function that if a condition is met, then it will run what is between these two curly brackets. Otherwise, if else it will run, it will test this, and if it's true, it will run this part. If not, it will test if this is true and will run this part. Actually, this is just to create the name file, the file name of the soil properties. Okay, so we just run this, and because we are working with soil attribute equal to soil organic carbon, okay, so it will run actually only this part. We can also run this, only this line, and that's it, and this is name of the file. So basically this is to write the final results using the ISO code of your country and the name of the soil attribute, and the same here. So, and with this we finish the script. Let's see the script number 4.2, 4.1. In a script, and this one, it has a bulk at the end of the name. So in this case, the script, it is very similar, but at the beginning, let me put this way. At the beginning, you can see that instead of having soil attribute, it has target soil properties. So here we have pH, potassium, soil organic carbon, bulk density, CEC, phosphorus, nitrogen. So if the previous script worked for you, then now you can apply this with all the soil properties. So if you have different soil properties here, you can change it.
Basically, same script with more.
It's the same script, and the difference is here in the line number 41. Another difference you will see in the line number 102. Sorry, 99, because it will run the whole script from modeling to create the model up to make the predictions for each of the soil properties. So it will run for each soil property. You see here, so it will go for each soil property. It will, well, I didn't create the soil property object, but the soil attribute object will change the name of the soil property every time that it finishes the whole script. At the end of this, if we go at the end, well, there is nothing. So all the steps that we did, part of what we did yesterday and part of what we did today, will be done in this for loop. What is the problem here is that maybe sometimes you might get an error and when the error is caused within the for loop, maybe you don't get too much information. So in the case that you get an error, then you have to see where was the error. So for this, you can say, okay, let's define here. We can comment this line, and then we say, okay, well, let's put soil attribute equal. We assign it to one of the soil properties. I don't know, for example, pH. And when we put this like this. So we put this like this. So then we can test if all the steps that are inside the for loop works or not. Okay. So if we find any error, we check. We have to change the script, and then remove the comment here and run the entire for loop. And this will take quite a lot of time.
So what about the physical properties? That runs a cell also? What does it chemical?
Basically, this is for the global soil nutrient map, and we define this as the target soil properties. But basically, you can predict any layer and any soil property in this way. They can be nutrients, physical soil properties, or chemical soil properties, and the 0 to 30 or 30 to or to any of the layers, the fixed layers, fixed depths that you want. Okay. So let's go back to the presentation. So okay, so this is the entire process that we did. We put together, calibrate the data from the soil and the covariates in a matrix. With this matrix, we created a model. This model that each model is for each soil property. So if we want to create a prediction of another soil property, we need to create a different model. Then we run this part in the script where we calibrate the model and produce the indicator of the accuracy. And then we make the predictions of the most probable value, that are the mean values, and the standard deviation that represent the error in a spatial, the distribution of the error in the map. So, and this is digital soil mapping, let's say. Okay, this is what we mean with digital soil mapping. Okay, back to R. There are two more files. So the work have been done. So now you have the layers, but the layers there, if their layers remain in your computer, nobody knows about this information. So we need to make a report. And for digital soil maps, we have to report some of the key components. In this case, we have two different two files. Let me just close this. Okay. We have two files here. One is the number 5 render report. It has some parts, but I'm more interested on the national report. National report. We open this file. You can see that this is a different, has a different extension. It is RMD. RMD are Markdown file. in an R Markdown file, you will see this icon here. It says knitr. So you can produce, for example, from this file, we can produce a document, Microsoft Word document, or PDF, or HTML document. So basically, here we have the file is organized in a different way. We have these things that are called chunks of code. So in this case, it's just part of the configuration of the file. Then we can write a part of the content. I will show you how it looks like, but basically all that you write outside the chunk doesn't run in R. And then what you have inside the chunk are the data. So in this case, for example, we will load the libraries of tidyverse, terrat, caret, and knitr. Knitr is the package that create tables and create this type of files. So in this case, it will go to the harmonized soil data. The harmonized soil data is it has the observation, so we can measure we can count how many samples we have for each soil property. So we load some other files, like this is a national report, and this is just a table. And we will, with this, we will create, for example, from here, it says, well, soil attribute, total nitrogen. You can write something about this map, the map about the total nitrogen, if you have it. In this case, we define the attribute that is the total nitrogen. And here we load the model of total nitrogen. Then here we run this part is already set up. I'm not going to go into the details of this, but basically what we have here is a file that when we compile, you can compile just clicking on the knitr and this icon. And it produced this document. So the text that is outside the chunks will create this. This is also part of the outside the chunk, I think. Let me check. Okay, no, this is the first table. So here we have data type, source, number of points. So it creates a table. Here is a table. This is to define the number of profile, the number of data that you have, the number of points, the source, the year of the samples, for soil profile data and for topsoil data. Then also for total nitrogen, you have the descriptive statistics. So the units, so you can modify, you can find these values in the actually in this part. If we go to the beginning of the total nitrogen, so here we have the model. This is the data. The soil attribute is the total nitrogen in this case, and it estimates so it creates a data frame with the mean value, and it takes the values of the original data and estimate the mean, minimum, median, maximum, a number of points, and the unit. So the unit was stored here. So and it creates the table. So and also then it will load the file that was predicted, that was produced. So this is the predicted mean, and also the predicted standard deviation. Then we also get the graph of the. This is a scatter plot with the differences between observation and predictions. All the attributes about the accuracy. So then we get the importance of the covariates. Of course, the document is not final, but these are all the elements that you need to report, to make a report of each of the maps. And then it goes to the next soil property. Okay, so with this you can create a nice report, and you can send it to a PDF, Word document, or HTML page. Okay, so this can be run from here, or the other, or the script number 5 will also run this outside from outside, basically. So you can set the working directory, define the file, the ISO code of the country. You define the path for the document, for the R Markdown document. Define the format of the output, and here's the output, the file name of the output, and then you render these parts, and it creates also the file. So these are some, and don't worry now, because we are at the beginning of the process. Now the important part is that for you is to start collecting the data, or if you have already data that legacy data, let's say, and that you can digitalize and organize to start producing the maps, then it is much better to focus on this and to focus on the script number 2. So the first step, I think that will be, this is the first step, is to be able to use your own data with the script number 2. So when you start this process, you may face issues. So then we met virtually, for example. We can set a meeting for discussing what are the problems, how to solve issues, and then we will fix each of the problems that appear, or how to organize the information, and so on. So every time that you include more data, more information, then you run the script again, and the first task will be to get the final result of the script number 2. This is somewhere here. The script number 2 was the first one that we used, where we ended up with this harmonized soil data. Okay, so this is the first task, and then we can, for the rest, we will have time to review again what were the steps and how to do it, and so on. But in this workshop, I wanted to complete all the material that we have, just to show you what is the road that we have to complete. Questions? Any question or comment or anything? I would like to send you the exam. Well, no, it's not an exam. It's just but from you to me. It's, I would like to send you a survey. Yes, it's not a test. It's not a test. It's just it's a survey to. Well, we always want to improve the work that we do. So I will send you a survey to. Well, if you have comments, it would be very good to know how we can. What you think that could be done in a different way, or share your thoughts. And finally, we were talking about recently with about the soil information system. One of the objectives of the project is to develop a soil information system. At GSP, we recently developed the Global Soil Information System. This is at this. I think it's already in this link. So basically, this has been developed by FAO for the whole organization. It's part of the initiative of Hand in Hand. You can search in Google Hand in Hand FAO. You will see the whole development, and this is a branch for GLOSSIS. So basically, this is a platform, an online platform that can hold different. It has these features. So it's a data catalog. Here we have a catalog about all the layers that are at the global level, but also we can hold the data for a country. So we can have a dedicated folder, or let's say a section for a country or for a region. So the data management and the distribution system is called CCAN. And then it also, the platform uses Terria. Terria is the front end. It has features like zonal statistics. You can create charts, side-by-side comparison, like you have in Google Earth Engine. So you can compare two maps, for example. You can export maps and views. It's really very. It has a lot of features that haven't done before in other systems. But so the task here will be to put all these parts together to create the CARSIS, the Caribbean Soil Information System. So these are part of the catalog. So in the catalog you have all the description, so the metadata, the owner of the data, what else? So you can, for example, create a copy of the view that you have in a PDF. Yes.
What resolution will that data be shown on map? Like, can use a global data set, right? So a small country like Grenada, we see the different soil types.
I mean, for this, we are in the early stage of the creation of the Caribbean Soil Information System. But for this small system, we are targeting to have a resolution of 30 meters. If the resolution is not, some countries maybe can have even higher resolution, other countries can have a smaller resolution. And what you can do is the good part of this system is that you can hold different layers, because actually you have a catalog, and the catalog is like in a server where it will bring with the WMS protocol. You can put all the maps together and the different resolutions. For the global map, I mean, for the global map, the global initiative, soil organic carbon map, is the potential sequestration of soil organic carbon, and those initiatives hold a unique raster at one single resolution. But you can still have the national maps in a different resolution. So it has some features like this. So this is what we plan to develop for the regional, but also for the national soil information system. We are still. This is a presentation about glosses, not about CARSIS, but this is just how do you say? A little bit of information about in the direction that we are going. Yeah.
Summary.
A preview.
Brief.
What do you mean?
Instead of how do you say like?
Yeah. No. Yeah. Sorry.
So it's new.
It's a fifth day.
Yeah.
No, it's a no. When you see the first part of a movie,
Trailer.
the trail. Yeah, the trail. Yeah. Thank you. Okay, so now yes, finally, and final step is to. I would like to show you the information about the situation of each of the countries with regard to the sampling scheme. So regarding the workshop, this is done. So this is all that I had to say. So in this table, yeah, in this table we have the situation of each country for the development of the sampling strategy. What we did is to use the soil maps and with the classes of the WRB or the USDA classes of the soil taxonomy and the land cover. We didn't use the DEM, but it could be used as well. Basically, here we have if the information that we have in this folder, in the share folder, is enough to produce the strata. So the application of the strategy that we are using is to use a stratified simple random sampling. So basically we divide the area to be mapped into areas in stratas. The strata, an stratum is an area that is considered homogeneous somehow. It doesn't mean that it's completely homogeneous, but it has less differences, less variation inside this unit that you might find in other parts of the land. So basically, we overlap the land use with the soil map. So then you have, for example, I don't know, some of the classes of soil for forest, the same class of soil for grassland, and the same class of soil for cropland. So then there you have three strata. So then we don't want to end up in too many strata. We target to have about between 20 and 30 strata. And then we distribute, these strata are used to distribute the points randomly. So according to the surface of each land unit, we distribute points. So with a minimum of 2 points per strata. Okay. So even for the smallest one, you can have still some some of the points.
So one question, I mean, this is out of curiosity. So is the points, like the sample points you generate, is random on the strata itself?
Yes,
Okay.
within the strata, yes.
Yeah, okay.
That's predicting the points based on the data.
Is predicting the point.
Yeah, based on the data. That
Yeah, this point is these points are defined in a way that it has to be used to go to the field to collect the sample, and they will be the observation that you use for feeding the model.
for
Yeah.
verification. For verification.
Not for verification, for calibration of the model.
Okay.
Yes, we did so basically those points will be, then you send the sample to the laboratory, you get the values from the laboratory, and then you use these values of the observation. It's the input of the.
So improve any model.
Yeah, it will be the input of script number 2. Okay. So let me show you one of the examples. So here we have each of the layers. I think that everybody has access to this. No? I will ask Triciana to share this folder. Yes.
Google Drive folder?
It's a Google Drive folder. It is in soil care.
Now we ain't got none.
So within data, we have, for example, Grenada.
I think that folder is fully, it is 100%.
Is one?
100%.
1% or
100% of.
It need more space.
Ah, okay, but but you can. I have enough space, so you can transfer the data to me. For example, using WeTransfer or by email or by any other Dropbox or whatever it is, so I can upload the data.
Okay.
So it doesn't take your space in Google Drive. So let me just open this project.
Inside. See, all the things is abdominals.
Okay, this is the case for Grenada. So here we have the soil map of Grenada. This soil map was aggregated. We aggregated some of the classes to have less amount of classes to end up with less amount of strata. So this map was intersect with this one. In this case, we have agricultural fields, forest, primary forest, and wetlands. I think, yeah, this is not.
There are some points that probably got water or probably some weeks and stuff.
Some water here. Yeah, but it's not. Actually, it's not considered. It's the color of the. Yeah, they were removed. So we only use this. Okay. So and then crossing these two layers, we got these stratas. Let me just this and this. Some areas, like the urban areas.
The GLM is FAO standard.
This is
FAO standard, right?
yes, this is FAO.
So in the 1980s, they did a map over to follow FAO standard.
These are the categories. The fluvial soils, clay soils. So the clay soils and fluvial soil are together. Here there are leptosoil, alluvial soils,
sorry, I get
Cambi soils.
some
And then you have this class of soils with agriculture. For example, this group of soils are with agriculture and forest. So these are the different strata that we ended up. Some of the strata were when you sum the area of all the small polygons, they were too small. So some of the strata were removed. So that's why you see some holes, and for example here. And also the areas that belong to urban areas were removed, or water bodies, they were removed. So in this map, we use this map to distribute the points. So we created two set of points. One is target points and the other are replacements. So, what is it? Sorry?
No, we just remember those points are fall in the highlands and the forest, deep forest, so like
Yeah.
no paths and you had traction.
We had a hard time finding something.
Yeah, finding, well, why we have target and replacement? Random points are very nice, but sometimes very difficult to reach. I mean, we could avoid some areas if we have a map of accessibility. So we could say, okay, this area is not accessible, so don't throw any point there because it will not be possible to be reached. At the same time, it means that you can make predictions with the process that we saw already, but it is very uncertain what is the real values because you don't have any validation point. Okay, you don't have calibration, but also nor validation for this. So basically these points, for example, let's go to this point, for example. So the points.
Any point. You see this? Right? What's in there? Nice forest, deep forest.
Number 12. Okay, number 12 belongs to the strata. Let's see. This is the strata. The strata is what is?
NTR.
Yeah, here it is. So this is forest. This soils under forest. Okay. So the number, oh sorry, let's keep it. So for example, we have the 12.1. Yeah, this is the point number 12.1. So this is the first point that have to be reached in this strata. Not in order of the logistic that when you go to the field, but this is in the list is the first point. What happens if you cannot reach this point because it's too far away, it's very inaccessible, it's impossible to go, or you don't have permission, or whatever the reason is, then we have this list of points.
Yeah, alternative.
So we go to the code number 12. So we have the number 12. So this is the point number 12.1. So this is a target point. If we cannot reach this point, we have to go to the first point in this list, the first replacement point. So the first replacement doesn't mean that will be just next to the previous one. This was the previous one. Now you have to go to this one. The point can be anywhere within this area. It doesn't mean to be just as close as possible than the other. Is again a random point. Why we are doing this? Why we are doing this in this way? You know, if you will survey only the soils that are near the roads, for example, the roads were built in areas that have some features of the landscape that were easier to make. I mean, the road doesn't go to areas that are very steep, for example. So, but when you want to have a map of the whole country that represent all the landscapes, you need representations for all the landscape types. So, and it is very important when you want to measure the accuracy of the map that the points are distributed randomly, somehow randomly. So then it is very important to go to the place where you have the correct point. So that's why we follow this strategy. So in this way we can be sure that all the landscape will be well represented. This is the reason to have such a complex or uncomfortable situation. So at the same time,
So one question.
yes, yeah.
So in the future, we want to maybe add more points to densify the thing. Can we use replacement as a way to increase?
Yes. Yes.
Yeah.
I mean,
But for different strata, say the strata itself, we don't find
Yeah.
not as because
Okay.
you feel the standard deviation, you want to get standard deviation a little stronger, you know? Can we use a replacement to strengthen the?
let me. Yes, we could. But if you want to increase the number of points, it should be done in a way that is proportional to the area of each strata. So is respecting the question.
The replacement point is just another point within the sample, or you get to decide on the replacement point?
The replacement will be
Generated.
it's already generated. You can
Points were just
the rule here.
The target.
So they're already preset.
All of them were preset. It was
Yeah.
basically if you can't get to the original one, you do the replacement.
So for example, here we have the strata number 1. The strata number 1 has 3 points,
You already got already.
and the first replacement had to be this. You cannot select any of these. You have to go to the first that was not used. After this is a rule. So then the rule here is it has strong statistical reasons behind this. So the idea is that you don't have any impact in the selection of the sites.
You have to be
Okay,
random.
you don't produce any bias in the
Don't
selection.
bias it, yeah.
It's to avoid the bias.
Or stratified, whichever way you want to make it.
And in cases where all the target points are inaccessible.
In this case,
particular
it might happen, for example, but we created 6. For example, we have
But then it have alternate
twice.
replace.
We created twice the number of points.
Somebody will make it.
Of target points, we created twice the number for replacement. So in this case we have 3 target points and there are 6 replacements. So I think that the 6 should be enough to complete 3 points inside the area. Okay. Yeah, let me show you one more thing. So if you want to apply this, here we have the folder script. There is these are well, it's not very tidy. I would say I didn't prepare them for giving a lecture, but if we open this,
He's a system.
you can
You create it out from where
Yeah.
Yes.
and you create it out from or
Let me check.
You pick one.
Barbados.
I'll just sort of file it.
Barbados. We don't have enough data.
after we set that.
What we need, I mean, if you don't have a soil map or you have soil map and you have land cover map, so let me check what is the situation. But before this, let me show you the very fast the script. Basically, so basically here is so here is how the soils were grouped. You see, so if you don't agree with this, you can say, okay, no, this group shouldn't be with that. So this is how the classes were grouped.
This is script 2.
Yes.
Script 2.
No, it's not the script 2. This is for Grenada.
So
Is within the data,
Or data.
Grenada and scripts. This is the grade strata for Grenada.
Strata spring.
What is that?
Well, they created their own structure for Caribbean types of soils.
that's based on what the
Yeah.
chemical.
There were two different maps.
Caribbean's an island.
Yeah.
Yeah.
Smaller.
Yeah.
And then, so well, here there are some reshaping of the data. So here we look. Yes, let me see.
What's all the letters?
So this is about the soil layer.
Just like the LVP.
Yeah, the LVL.
That's the FAO salt type, right?
Oh, okay.
The one salt, in 1980, they standardized the salt types in the FAO standard. So I
Okay.
guess they use that.
So then based on these
Yeah,
characteristics
yeah.
in the soil, it would give this the strata its name.
Some countries actually use USD, some use FAO. We have FAO.
So
this
was
Yeah.
We need to take notes.
this is the original soil map of Grenada. Okay, and these are the different fields within the shapefile. So here is the reshaping the data of the soil. Then we have the reshaping the data of the land cover. And then is the process to create basically the areas. So once we created the strata, then this is the stratified simple random sampling methodology. You can see this methodology in this link. I mentioned this the first day. This is a book from Dick Bruce, a statistician from the Netherlands. He prepared this book. It's sampling, spatial sampling with R. It has, I don't know, hundreds of methods. But still, this method is one of the easiest to apply and very versatile because you can use it for mapping or for validation of the map. So here you have all this explanation. You can access this chapter. That was, yeah, this is just an example. I will not go through this, but if you are interested, if you want to have a session to review the script, we can do it. Okay? This is the idea.
So, all the class, all costs on class. Is it different family?
Wasn't part of that process.